Alright, in this video we're going to be practicing our washer volumes in AP Calculus, and I'm going to be working through the 8.2 extra practice specifically for washers. And in this video I'm going to just set up the integrals and not actually compute them. I might tell you which of them can be computed by hand and which of them are going to need a calculator, but I'm just going to focus on the setup because that's, in my opinion, the challenging part. Okay, so we're going to start off with this region R, which is bounded by the graph of 1 plus x cosine x and y equals 1. Okay. We've worked with this region a bunch in these extra practice sets, and so we know that this intersection here is happening at x equals pi over 2. If you need to verify that for yourself, you're going to set those two things equal to each other, solve for x, and you'll see that x could either equal 0 or it could be pi over 2. Really any other place where cosine equals 0, but we're only looking at a very small picture of that graph. Okay, so we're going to start by rotating R around y equals 3. So I'm going to follow that same three-step process as always. I'm going to make a sketch, label the sketch, fill in the formula. Okay. So here's R, and there's y equals 3, going to be fully above the line, above the region, which means that we're going to need washers. Okay. So I'm going to go here. I'm going to start at the axis of rotation and draw my large radius all the way to the far edge of the region I'm rotating. Okay. I'm going to write down a formula for it. Since that radius was sitting vertically, it's going to be a top minus bottom type situation. On top, I have y equals 3. And on bottom, I have y equals 1. Okay. Then for the small radius, I'm going to start at the axis of rotation, and I'm going to reach to the near side of the region I'm rotating. And I'm going to say B is also going to be top minus bottom. Top is y equals 3. Bottom is y equals 1 plus x cosine x. Okay. Now we know that volume is equal to pi times the integral of large radius squared, so that would be 2 squared, minus the small radius squared. Now the small radius is 3 minus 1 is 2, minus x cosine x. And we're going to integrate as x goes from 0 to pi over 2. Okay. This one would require the use of a calculator, that x cosine x thing. We will get to a point where we can anti-differentiate x cosine x. I'm not sure about x cosine x, or x squared times cosine squared x. That doesn't seem as promising. That was number 1. Second one is we're going to rotate R around the line y equals negative 2. Okay, so it's going to be pretty similar, but I'm going to sketch my region, sketch the axis of rotation, which is definitely going to be below. It doesn't matter how far below. Drawing doesn't have to be to scale to, get the right idea. So you start the axis, reach to the far side. It's a large radius. Large radius is going to be top minus bottom. That's y equals 1 plus x cosine x, minus the bottom is negative 2. Okay. Then B is going to be, top is y equals 1, bottom is y equals negative 2. And then we're going to fill in the formula. The volume is the integral of pi large radius squared minus small radius squared. Okay, that's 1 minus negative 2 is going to be 3. Minus the small radius squared is going to be 3 squared. And still as x runs from 0 to pi over 2. Now we're going to take this u and v region. U and v are kind of both bounded by y equals x to the 4 plus 1, and y-axis, y equals 1, x equals 1. Okay, so first we're going to start by rotating u around x equals 2. Alright, so I'm going to make a sketch of u. And I might label a little bit. Y equals 2, and this is x equals 0. Okay. Then I've got x equals 2, which is, I don't know, maybe going to be right there. Large radius will be all of this. And I might need to label this as well, right? Got to label that sketch. Okay, that's going to be A. A is sitting horizontally now, so I'm going to need to write A as right minus left as the difference of two x coordinates. And I have this as y equals, so I'm going to need to solve for x. Down here, I'm going to have, well, I guess I'm not going to need it on this one, and I'll come back to that. A is going to equal, right is x equals 2 minus left is x equals 0. Okay. Now to get the small radius, that's where I'm going to need to solve for this. Okay, x is going to be the positive fourth root of y minus 1 because we're over here in the first quadrant where x is positive. So I'm going to, let's see, what am I going to do? Oh, I'm going to draw in my small radius. Okay, and it's going to be right minus left is x equals 2 minus x equals the fourth root of y minus 1. And then I'm going to set up my volume integral. Okay, large radius squared is going to be 2 squared, minus small radius squared would be 2 minus the fourth root of y minus 1 squared. dy, and y is going to run from that intersection point happens at y equals 1, because x equals 0 and y equals x to the 4 plus 1. And it goes up to y equals 2. Okay, number 4, we're going to rotate u around the x-axis. And then we're going to rotate around the x-axis, which is completely separated. So this is going to make the definite washer situation. So I'm going to start the axis, go to the far edge. That's going to be the large radius. Top minus bottom. Y equals 2. The x-axis says y equals 0. And the small radius is going to be top is y equals x to the 4 plus 1 minus bottom is y equals 0. Okay. And volume is going to be pi times the integral from x equals 0 to x equals 1 of large radius squared minus small radius squared. Okay, number 5, we're going to rotate v around x equals negative 2. Okay, we'll do that. V is this part of it. X equals negative 2 would be over there. And, okay, so this is going to be, I mean, it's y equals x to the 4 plus 1, but if I'm rotating around a vertical axis, I'm going to need to solve for x anyway, and I've already done that to 1, so I might as well say x equals the fourth root of y minus 1. And then this is going to be x equals 1, and that would be y equals 1 up to y equals 2. So we already know that. Right. That large radius is going to be right minus left. What's negative? Yeah, x equals negative 2. And then my small radius is going to be right minus left is fourth root of y minus 1 minus negative 2. Okay. And then volume is going to be pi times the integral. Large radius is going to be 3 squared minus the small radius is the fourth root plus 2 squared. We're going to let y go from 1 up to 2. All right. Number 6, we're going to rotate v around the y-axis. And this is touching the y-axis right there. Not that it really matters as far as your sketch. As long as you didn't put it right there, that would be the wrong thing. So start at the axis, go to the far edge. And on the right I have x equals 1, on the left I have x equals 0. That's y-axis. Then over here, small radius. I'll have on the right, I'll have x equals the 4th root of y minus 1 minus x equals 0. So the volume is pi times the integral. Now we know y is going to run from 1 to 2 because we've done a couple of these. Large radius squared minus small radius squared. This is one I could see you being asked to do, okay, by hand. Because it would be, okay, you square the 4th root, you're going to get the square root. We can anti-differentiate both of those things, you know, relatively easily without a calculator. And so this is one that you could potentially be asked to do on your own without a calculator. Right, now 7, 8, 9, and 10 are going off of this set of regions right here that are bounded by the coordinate axes, x equals e, y equals the square root of e minus 1, y equals log x, and y equals the square root of x minus 1. Okay, there's a lot I can do with that. Okay, so we're going to start by rotating b around the x-axis. So I'm going to draw b. I'm going to label it. And this is y equals log x. And then this would be x equals e. Right. And that's at x equals 1 right there, which you can see on the problem set itself. Anyway, all right, so we're going to rotate b around the x-axis, which is going to be right there. Okay. A is going to be top minus bottom is square root x minus 1 on the top, minus the bottom is the x-axis, that's y equals 0. B, that'll be y equals log x minus y equals 0. Okay, x went from 1 up to e. A squared is going to be, well, just x minus 1. Not plus. Definitely not plus. Where's my eraser? There it is. Minus. Okay, and although this worked out really well, that is not going to be something that we have an antiderivative for in this class, so yeah, we're not going to be able to do this one by hand. This would require a calculator. All right. 8, we're going to rotate c around y equals 1. Okay, yeah, that's okay. Okay, so c looks like this. Y equals 1 is going to come through right there. I'll label this. C is bounded by y equals log x. And then that's y equals 0 right there. Okay, and then that's x equals e. Might even label that also. Okay. y equals 1 minus y equals 0, top minus bottom. Okay, and then b is going to be top minus bottom, so y equals 1 minus y equals log x. And then volume will be pi times the integral, as x is still running from 1 to e. Large radius squared minus small radius squared. And again, because of the natural log, it's going to require a calculator. Find the volume of the solid formed by rotating A around x equals -1. All right. Okay, so I'm going to that's going to be A. This is y equals the square root of x minus 1. This is y equals the square root of e minus 1. And that's y equals 0. Okay, well, we can see that's coordinate axes. We're going to rotate this around x equals -1, which should probably be about there. Okay, so in doing right minus left, I'm going to have to say, all right, well, if this is x equals -1, I need this as x equals, so I'm going to square both sides. And then I'll get x equals y squared plus 1. Right, so A is going to equal right is y squared plus 1 minus left is x equals -1. Okay, so that'll be y squared plus 2. And then I'll get my small radius. Okay, on the right I have x equals 0, and on the left I have x equals -1. I can combine these inside my volume. Okay, y is going to go from 0 up to the square root of e minus 1 right there. So, okay, and then large radius squared would be y squared plus 2 squared minus, well, that's going to be 1 squared. Okay, this one, yeah, mostly because of that, I wouldn't see that one being one you'd be asked to do by hand. Right. And then number 10, we're going to rotate b around x equals 3. I don't think we are. I think that was ill-advised. Yeah, that's going to be troublesome to say the least. It's one that would be much better off using the shell method, but I'll warn you that this is not one that you would have to do in AP Calculus, but it is still workable. It's just going to require a second integral. Okay, and I'm going to need another color too. All right, so I'm going to draw B. And I might draw a little more exaggerated version of it so that you can see what's going on here. All right, yeah, about like that. Okay, what we're going to have to do is we're going to have to, because we're rotating this around a vertical axis, which is x equals 3, which is over here a little bit bigger than e. Okay, we're going to have, if we draw a radii, we're going to see we're going to have, you know, large radius running here, small radius running here, but then up here the small radius changes right after this curve ends. So we're going to have to split this scenario up over, actually maybe I'll see if I've got orange. Or this is bright enough, this is pink, this will work. Alright, we're going to have to split this up here. Okay, and we're going to have to split it into 2 different scenarios. But we can work with that. Okay, this is y equals log x, so x equals e to the y. Okay, and this is, we already solved this one backwards. This was y equals square root x minus 1, so x equals y squared plus 1. And we should be able to do it now. All right, so the first large radius is going to be this. It's going to be right minus left. Okay. And B1 is going to be right minus left. Now, A2 up here is going to be the exact same. Right, I'm still going from the curve x equals y squared plus 1 over to x equals 3. So I'm just going to say A2 is also equal to, hold on, what's going on here? Yeah, 3 minus y squared plus 1. But then the small radius up here, once it changes, that's going to become right minus left, x equals 3 minus that vertical line happens to be x equals e. And so I'm going to have to, do these two separately and add them together. So volume equals y runs from 0 up to the y coordinate of the intersection. Well, that's x equals e to the y, and and x equals e right here. Y equals the log of x, so that's going to be y equals 1. 0 to 1 of 3 minus 1 is 2 minus y squared minus small radius squared 3 minus e to the y squared dy. And then we're going to have to add another volume integral, except this one will start at y equals 1 and go all the way up to the top, which is the square root of e minus 1. Okay, and large radius squared will be that same thing, so 2 minus y squared minus the small radius squared is now 3 minus e squared. Okay, and that was kind of a lot, and like I said, probably beyond the scope of AP Calculus, but, not a bad problem. All right, we've got two more. First one, and these are going off of D, E, and F, which are just D and E, I suppose. D and E are bounded by the graphs of y equals 2 minus cosine x, y equals cosine x equals 0, and x equals pi over 2. So we're going to rotate D around the x-axis. That's y equals 2. That's the x-axis, or the y-axis, which is x equals 0, and we are rotating around the x-axis, which is y equals 0. Okay, A is going to be top minus bottom, and B is going to be also top minus bottom. So 2 minus cosine x minus 0. Okay, volume. Okay, x is going from 0 to pi over 2. Large radius squared minus small radius squared. Okay. And this one definitely looks like 1.0. We could expand this with some algebra and, square that and actually do the subtraction and everything. And, you'd end up with something with cosine x, but you'd also end up with something with cosine squared x, and that's not an antiderivative that we're required to know in this class. So you would need to either use a trig identity or a calculator, and well, I'm not going to do either of those things in this video. I'm just going to be setting up these washer volumes, as you've seen. So, number 12, find the volume of the solid rotated in E around the y-axis. Okay, wasn't exactly looking forward to that, but it's okay. This one's also going to require two integrals. Okay, so I'm going to have to split it up like that. Now, if you are seeing that this whole scenario is like really symmetric, that 2 minus cosine x versus regular cosine x, you could just do one of these and then double it. I'm going to do both of them just to show you how I would set that up if I had to. And we're rotating this around the y-axis, which is right there. Okay. Now I'm going to label these y coordinates so you know what's going on here. And if we're rotating, okay, that's A. And this A is always going to be the same. A being right minus left. This is x equals pi over 2. On the left, that's the y-axis. That's the set of all points where x equals 0. Okay. Okay, B1 is going to be on the right. I've got, well, if y equals cosine x, so what I can do is over here. X is going to be arc cosine of y. So, the arc cosine y minus 0. And then B2, I'm going to have to do a little solving to get that. I can work with that as well. That's y equals 2 minus cosine x. Okay. So maybe I'll solve for cosine x equals 2 minus y. Okay, and I'll take inverse cosine of both sides, and x is arc cosine 2 minus y. Okay, minus 0. Right minus left. Okay, then I'm going to write down my volume formulas. I guess it's one formula. Okay, first one, y will run from 0 to 1. Large radius squared minus small radius squared. B1 is inverse cosine y. That's not going to be an antiderivative, we know. I'm just going to warn you right now. And then I'm going to add that to the integral from y equals 1 up to y equals 2. Whoops, there should be a pi there. And, okay, the large radius is staying the same. Now the small radius has become this. So, and that's an expression for my volume. Okay. And that's all for this practice set. Thanks for watching.